Hi, this is Alex from devstories.eu. High Performance Python Async, episode 13 of 17. You need to export a 1 million row user table to a file, so you run a standard database fetch. Suddenly, your Python application eats up all available RAM and the server crashes. You cannot pull massive data sets into memory all at once, which is exactly why we use streaming results with cursors. Normally, when you execute a query in asyncpg, the entire result set is pulled across the network from Postgres and held in Python's memory. The database builds the complete response, ships it, and asyncpg constructs Python objects for every single row before your code can process the first one. This is perfectly fine for 50 rows. It is an immediate problem for 5 million rows. To avoid crashing the server, you need to sip the data rather than gulp it. A database cursor gives you a pointer to the query results on the Postgres server. Instead of pulling everything, the cursor allows your Python application to fetch the data incrementally. In asyncpg, you do this by calling the cursor method on your connection. You provide your SQL query and any required arguments. This method returns an asynchronous iterator. You write an async for loop to iterate over this cursor. Under the hood, asyncpg automatically fetches rows in small, manageable batches from Postgres. Your code processes a few rows, writes them to your export file, and moves on. Python cleans up the old rows from memory, which keeps your application's total memory footprint completely flat, no matter how large the table is. There is a strict rule here that trips up many developers. If you try to iterate a cursor directly on a standard connection, asyncpg immediately throws an interface error. The error message will state that cursors cannot be used outside of a transaction. Here is the key insight. PostgreSQL cursors are structurally bound to database transactions. When a transaction commits or rolls back, PostgreSQL destroys any active cursors associated with it. By default, asyncpg operates in auto-commit mode. This means every individual query you run is wrapped in its own tiny and visible transaction that closes the moment the query finishes. If asyncpg allowed you to open a cursor in auto-commit mode, that implicit transaction would end instantly, and PostgreSQL would kill your cursor before you could fetch a single row. To make cursors work, you must explicitly manage the transaction boundary. You do this by opening an asynchronous context manager using the transaction method on your connection. Once you're safely inside that transaction block, you call the cursor method and start your async for loop. Because the transaction stays open for the entire duration of the context manager block, your cursor stays alive on the PostgreSQL server, allowing you to stream all 1 million rows securely. There is one rare exception to this rule. PostgreSQL supports a feature where you can declare a raw SQL cursor with the phrase withhold. This tells the database engine to materialize the result and keep the cursor alive after the transaction completes. Doing this eats up database resources, and it bypasses the efficiency of standard streaming. For almost all streaming tasks in asyncpg, the explicit transaction block is the required approach. If you find these episodes useful and want to support the show, search for devstories.eu on Patreon. Remember that a cursor transforms your database interaction from a massive, risky memory allocation into a controlled, persistent pipeline that can safely process any volume of data. That's all for this one. Thanks for listening and keep building.